Oh, it's time. Okay, so the next speaker is Vladimir Temlyakov from South Carolina now.
Now, yeah, literally from South Carolina.
Yeah. Sampling, discretization, and entropy. Please, Volodya.
Okay, thank you, Boris. So, as you know, we are talking on this workshop about sampling discretization. And in my talk, I will, first of all, try to make a connection to some known things. And for instance, and probably this will be the main part, to learning theory. But the kind of alternative goal is to discuss the following question. So we are talking about sampling discretization with the same weights. And as you saw from the talk by Feng, that in that case, we impose some restrictions on the subspace. So the question is in which terms to impose those restrictions. And it turns out that the entropy is the right terms. And I will explain this on the connection with learning theory. So let me begin. So two settings. Right away, we distinguish two important settings. One thing which was already discussed in Feng's talk and also discussed in Gideon's talk, that when we discretize LP norm or LQ norm of elements of a given n-dimensional subspace. So, and we call this Marcinkiewicz type discretization theorems or Marcinkiewicz-Zygmund inequalities. But the important thing here is the subspace is n-dimensional. So in some sense, this dimension n and then the number of points which we need, they are kind of related. Another point is functions which we want to discretize belong to some function class. And this function class could be a subspace on infinite dimensional space. So certainly in this case, we cannot prove results like we proved in the first case. That means I would say this kind of relative errors, but still this is a very important example. So, and I will begin with the second when we are talking about the function class. So here is the setting. So function class, so this is W, the function class what we want to consider. And as usual, this LQ will be the LQ space on the omega. This is the set, and mu is a probability measure. So this is standard assumptions. And now two quantities. The first one, we discretize the LQ norm using the same weights 1 over m. And then we take supermum over the whole class. So this is the worst case for the whole class. And then we optimize all the points. And the second one, we do the same, but instead of 1 over m, we allow the weights lambda j. And in that case, we minimize over both, over these points and all the weights. So in this setting, this error is a kind of absolute error. That means this error depends only on the class, but does not depend on any specific function in the class. So this is opposite to the n-dimensional subspaces. You will see this later. So, and as I already mentioned, and this is even in the title, that the key ingredient here is the property of this class, which are expressed in terms of entropy. So let me illustrate this on the following theorem. But first of all, this epsilon entropy numbers, and this is a standard definition. The only maybe point to attract your attention to is that we assume that the points belongs to the class. This is not important because in the sense of order, it does not change anything, but it is convenient. So and here is the theorem. So assume that the class, and that was for real functions, but it's not that important. Assume that this class W satisfies the following conditions. So all the functions are bounded in L infinity norm. And for simplicity, let's assume that this class is embedded into the space of continuous functions. So, and then we have the following relations. If the entropy numbers of this class in the uniform norm, L infinity always stands for the uniform norm, decays like this under this assumption on R. Then we guarantee that this arrow, I mean with the same with equal weights, 1 over m, decays in the same rate. So one can look at this theorem as a sort of variant of Karl's theorem. If you know, I will not formulate this as an inequality because basically the Karl's inequality stays the following. So if you know that Kolmogorov width, some people call decay with this rate, and there is no restriction on R is positive, then we guarantee that the entropy numbers decay with the same rate. I mean, the upper bound is the same. And here we have the same property, but if you see here, there's the entropy numbers in the uniform norm, but the arrow is in L2. But anyway, this is a general result in the style of that. So what are these restrictions? Let me make some comments. So
may I ask you the question? I'm sorry. Your quantity is related with the arrow of Kubachev formula, or not?
Sure. Yeah, it is. It is exactly the Kubachev formula, but for very special kind of set. This is not the unit ball of the L infinity for all, like the subspace.
Yeah.
But this is f from the class, but we apply the Kubachev formula to the function which is taken absolute value of function and raised to the exponent q. So this makes the problem different. Yeah, but this is certainly, if I have time, at the end I will give more precise connections with numerical integration because it's obvious like this, but we can prove some theorems in that direction too. But if I have time, I'm not sure in that, but let's go ahead. So, and as I already mentioned that it is well known that in learning theory, the entropy plays a fundamental role in many kind of estimates. So I will explain this in more details. And those methods which people use in learning theory, they are restricted to this, R less or equal than 1/2. So this is why we basically have in theorem 1 the restriction for R less than 1/2. Basically, that theorem, which I just formulated, theorem 1, is a more or less direct corollary of one of the results of our joint work with Sergei Kanin. And this I will explain. And this is an open question. It would be interesting to understand if this general relation, as I said, in the style of Karl's inequality, holds for all R, not just for R less than 1/2. Because when you look at this, it's not quite clear why, in the formulation of this theorem, why R should be, R equals 1/2 should be kind of a borderline. So now a little bit about the learning theory. So I do not expect everybody to know the basics of the learning theory, so I will briefly give the introduction. I should mention from the very beginning that ideologically, in a sense, this learning theory approach and what we have in discretization are different. But it turns out that the method which we use could be the same. Because in learning theory, basically our assumption that we do not know this measure rho. We do not know, but nonetheless, we want to do something. But in our case, we assume that we know that measure mu. So this is a big difference. But anyway, as a probabilistic technique or statistical technique, the same technique can be used. So this is the setting. So we assume that x is like that omega, which we had before, but this is standard notations for learning theory, so I keep them here. And y, these are function values. So this is function f maps x to y. And we define the arrow. So this is the arrow. So the integral with respect to this rho, and rho is a measure on this, on the direct product of x and y. And related to this concept is measure rho x, which is called marginal probability measure. In a certain sense, it is a projection of this measure rho on this RG on x. So, and this is strict definition. And then we define this function, and this called is a regression function, the conditional expectation of y when x is fixed. So it can be defined explicitly, but it is a function. And the problem is of learning theory is that we have some data, so some xi's and some yi's, and we want to approximate this f rho x. So if you know everything, and then this f rho is the best over here. So this minimizes this one. F rho is comparatively easy to understand. I will not talk about this in more details, but anyway, if you know everything, that means if we know this integral can integrate this, then that f rho is the best, But we don't know that integral. So what we know, we only know the data. So x1, xm, and the corresponding values, y1, ym. It's not even a function. That means this is just a distribution of these points in Rd plus 1. So then you want to approximate this f rho. There are different ways to measure this quality of approximation. One standard thing is to measure this in the sense of expectation. But another one, which is more accurate, to do this using the probability, that means using the distribution function for that probability. So, and standard assumption that we assume that all these are independent and distributed according to that rho. So this is the setting. So now this estimator fz, basically this error what we need is the error, the difference of this measured in L2 rho x naught. So this is what we have. So now we define the empirical error. So this is exactly what we can calculate on the base of the data given. So this is the one. So, and now as you can see, it is a discretization, exactly a discretization of that integral which what we had before. So basically, on the base of that, we replace the original one by this one, and then the method is to minimize this one over this f rho and get this as an approximation. So, and for sure, for this method to work, we need to guarantee that this one deviates from the original error not much. And this is the concept of defect functions. So this is exactly this difference. So it is a random variable because g is a random variable. So we are interested in this. So now kind of assumptions. Certainly we assume that this w, usually there is standard assumption that this class is class of the function of the regression function such that we have this property. That means for all y's in our this y capital, and for all f and all x, we have this bound. And again, it's standard assumption. So, and under these assumptions, we proved with Sergei Konягin the following theory. So if this class, the class of regression functions, so certainly you can ask the following question. So if we begin with rho, let me go to the very beginning. If you begin with rho, that it would be natural to make some assumption on this rho. And we do make assumption on this rho, but not directly. We make this assumption in terms of regression functions. So we associate with rho a regression function f rho, and then say that some property are satisfied if f rho belongs to the W, to some class. And here is the theorem. So if this class is good enough in the sense of entropy numbers in L infinity in the uniform norm, so decays like that, then we guarantee that the supremum, and this is distribution, I mean, we could write this similar bound for expectation, but we are interested in this. So the supremum of this, so this is exactly what Gideon already mentioned. We take a supremum over the class, and now we estimate some probabilistic characteristic of this random variable. So, and here is a bound. Here is the bound. So it's written in this way. And this is 1 over r. So one can easily convert this theorem into that theorem 1, which I formulated. Again, in a sense, this theorem is a more deep result, because here we do not assume anything about, we do not know actually, we do not know that rho. But in our discretization result, we usually assume that we know the measure mu. But anyway, so this is the connection to the learning theory. Let me talk a little bit about this n-dimensional spaces. But anyway, the conclusion from this part is the entropy numbers are very important in learning theory. And clearly, this is not the first result in this area. So that was well understood clearly well before us with Sergei Kanyagin. And the entropy numbers were used a lot in the results of like this in learning theory. Now let's return to this the first question about two types of problems, the Marcinkiewicz type problem. Then when we have n-dimensional subspace, so the subspace has a finite dimension, and we are interested in these inequalities. So in this case, this problem depends on 4 parameters basically: m, q, and these 2 constants. So clearly it could be reformulated in different ways. It could be like 1 minus epsilon here, 1 plus epsilon here. But as a matter of fact, in some cases, in some results, we can do this. We can prove this with constants, but we cannot do this with 1 minus epsilon and 1 plus epsilon. So I would certainly prefer to keep this in this form. In the case q equals infinity, but I will not be talking about this. But anyway, this is the setting. So this is obvious. So what we need to satisfy this inequality. And it's just a notation, but pay attention to this. So if you write that xn belongs to that, that means that this discretization holds. In this case, with 2 constants. In this case, will be just 1 constant. And now some results. Some of these results have already been formulated by Fengdai in his talk. But I will repeat some of them and add some other results too. So let's begin with L1. So in the case of L1, in 2017, the following result was proved. So now, as a class, we consider the unit ball of this subspace and the unit ball in L1. And now we impose our conditions, our assumptions on the entropy numbers, again in the uniform norm, and of this compact set of X1, the unit L1 ball of the subspace. I write this in this form, this one and this one, but as a matter of fact, this one is not needed, because if we have this, actually even just for k equals n, if you have this inequality, then very standard result in the entropy implies this one. There is some constant in front, but doesn't matter, this order. So in a sense, this is the only assumption needed. But just for completeness, we formulate this one. So if the entropy numbers decay with this rate, and you may ask why you write in this way, n over k, but it will be clear later. So, but anyway, if it is satisfied, then we guarantee then there exists a set of m, and let's look at the upper bound for this m. This is n, the dimension, this same parameter b, which stands here, and then some extra logs, log squared, but anyway, this is log factors. So, and this point such that we have this inequality. We can specify this 1/2 and 3/2. We could make it closer to 1, but then this clearly constant will depend on those parameters which are here. So this was in L1. And the technique which was used in the proof of this result was actually the chaining technique, which we used with Kanyagin in the proof of that theorem which I just formulated. So this also makes the kind of connection. So if you use that same technique, the chaining technique, then we can prove that. But that, I would say, straightforward chaining technique did not work for LQ, Q greater than 1. For L1, everything was fine. That means we got these logarithmic terms. But if that same technique would be applied for LQ in a straightforward way, then instead of n, here we would get something like n to the exponent 2 minus 1 over q. So for LQ, and this is the paper of 4 authors, Feng Dai, Andrei Primak, Alexei Shadrin, myself, and Sergei Tikhonov, we extended, or we proved the result is the same for all q between 1 and infinity, but the technique of the proof is different. It also uses the idea of chaining technique, which, by the way, goes back to Kolmogorov, who suggested this in 1930s. But the realization of that technique is very different. So, and this allowed us to get similar result, but for all q, including 1, but in 1 is the same result, but for all q strictly less than infinity. So again, let's look at this and read. What is the difference here? So when we introduce q instead of 1, we require the bound of this form, 1 over q. Again, one of this form is kind of, for you now, it's maybe not clear, but it's very natural to formulate assumptions on the entropy numbers of the unit ball in this form, n over q to the exponent 1 over q. And then the result is similar. So then m is bounded by, I mean, we can find m which is bounded by n b to the exponent q and some logarithmic factor, and this is log to the exponent 2. And that same inequality. And we don't know, maybe there is some other way, some other technique, even with this assumption, which could allow us to either reduce this exponent to the smaller one or to cancel this all together. And for some q, which is q less than 2, there is indeed a technique, and I will comment on that later. But anyway, this is the one. And some variants of that technique. Again, as I said, these entropy numbers in L infinity, basically this idea comes from learning theory. But if you look back at that, why that was important in learning theory? Because remember that rho, what I mentioned, we did not know that rho. So somehow to impose restrictions in terms of rho, which we don't know, and you want the result to serve for all rho, then L infinity norm is very good in that sense, because L infinity norm doesn't depend on that rho. So, and this is basically the explanation, and it is a right explanation in a sense. But as to L infinity, again, it was known and well known in like empirical processes, which was developed like 30, 40 years ago, that L infinity norm in some of the results can be replaced by a little bit weaker norm. But let's talk about this weaker norm. And Yegor Kosov applied these ideas in discretization and got, in a certain sense, stronger results. So what is the idea? Instead of L infinity norm, when we take supremum over all arguments, we say, let's fix some set of points and take supremum only over that set of points. So certainly we have this inequality. And we can formulate the concept of entropies in this, it's not a norm, but in this semi-norm, for entropy numbers, it doesn't matter either it is a norm or a semi-norm, we can make a definition. So, and it turns out that with restrictions on this weaker norm, one can get similar results for discretization as what I will just formulate. So let me formulate this result. This is the result by Yegor Kosov. And let's look at this carefully, because some little wrinkles require attention. So what we have, let's do this backwards. The final result is the same. We have discretization with equal weights. Now, what are restrictions? Restrictions are here. And the restrictions, as you can see, in a weaker norm. certainly if we have that restriction for L infinity norm, that we have that restrictions for any ym. This will be the same restriction. And in that case, if there is no ym but L infinity, this would be a restriction for the previous theorem, from this theorem, But here it is weaker. It is weaker assumption. But we are paying price for that. So if you look now at the restrictions for m, then you can see that m is to the main part, n multiplied by b to the q is the same. So the main part is the same, but logarithmic term, and in many, let me just kind of deviate a little bit, in many of the results which we are working on now, we are fighting for optimal, or actually the smallest exponents for the logarithms. So basically in the direction what just Gideon mentioned, that his first open problem, what are the best, or in many cases we don't know if these logs are needed at all. But anyway, so but in this case, if you look at this, for 1 it is 2, like it was in the very first theorem for L1, this is the same. But for Q less than 2, here we have 2 minus 1, so this will be 1. And in that theorem which I formulated, it was 2, so it's better by 1. But for Q greater than 3, for instance, if you look at this is Q. If Q greater than 2, it's Q, but this Q minus 1. So this grows to infinity with Q like Q. And in the previous results, with that technique with L infinity here, it is just 2. So it does not grow with Q. And in some application, this is important. But anyway, let's keep going. Now, after we have these conditional results, which are of the following type. So if the subspace has the unit ball in LQ norm, which satisfies the certain condition on entropy numbers in the uniform norm, then we guarantee existence of good discretization. So the next question is, under which other conditions we can prove the entropy numbers conditions? And here they are. So if you have these two conditions, and this is what Feng Dai already mentioned in his talk. So if you have the Nikolsky inequality, and another condition which basically allows us to interpret L infinity in a certain sense as LP norm, then we have the corresponding entropy numbers inequality. So this is what we have. And now I'm returning back to that my remark, why we are writing those conditions in this form. Because it turns out that these natural conditions, which are like Nikolsky inequality, and this is not that minor condition, but still it's different condition. Many of those subspaces which we consider, they satisfy that. So if you have this Nikolsky inequality, then we get this, And as you can see that B, which was in front of that, it has order of log n to 1 over q. That means logarithmic order in n. Now the next thing. So this is what, like a lemma, again, due to Yegor Kosov in that same paper, which I already mentioned, that so if q is between 2 and infinity, that it turns out that this inequality, again, Nikolsky type inequality, but it's different one because LQ here, it's not that inequality like before, because before, let me return back and stress this. So this Nikolsky inequality here is just for the pair infinity and 2. But the result here is for all q between 1 and 2. That means one Nikolsky inequality for a pair infinity and 2 serves and covers the whole this range for q. We get the result. But here is for specific q, we have a specific Nikolsky type inequality. And as a result, we get this. We get this one, and for a weaker L infinity norm. So certainly it would be nice for us to have this without this ys here, but we cannot do that. And under some extra assumption, we can do this. But again, Nikolsky inequality implies some of this. And if you look at this, in a sense, this is close to what we need is k to the exponent 1 over q. or -1/q. But how these things are related? So this empirical processes norm like this and this norm. It turns out that this is very simple remark. It's nothing deep in this. So if we have that same Nikolsky inequality, and in addition to this inequality, we have this. That means we have discretization in L infinity, and the number of points for the discretization is polynomial in the exponent n. It is a restriction because in general, and this is what you probably will learn from Boris Kashin's talk tomorrow, that it is a restriction, and in many cases we need exponentially in n number of points for good discretization at L infinity. But anyway, again, in many examples we have this restriction. So in that case, if you do have, we have this inequality like in the previous one, and with a stronger norm, L infinity norm, instead of that empirical processes norm. So now one comment. So about this, because this result, Kosov's result, is actually a deep result. It is based on deep results from function analysis and specifically on some Lagrange inequality for entropy numbers. And let me formulate this in more details in order to make sure that you understand what's going on here. So this is a notational thing. First of all, for a Banach space, we introduced this, the concept of modulus of smoothness. It is a standard thing, so nothing difficult here. But now we are playing in n-dimensional subspaces. So what we do, we say that let's have a system of elements and then take the linear span or span of this dn and introduce this norm. So it's like kind of a norm. If these are trigonometric polynomial, trigonometric functions, this would be a norm for the function. And this is why we write this a here, or a1 dn. So this is by the definition. So this is infimum of the sum of absolute value of the coefficients for the representation like that. And then we take a dual one, a dual norm to this one. And this is written here. So this is the one equipped with this and this and that. So, but then, and this is the deep result. It is a non-trivial result, a very non-trivial result, which Talleyrand proved in 1995. You can find this in his book. So it claims that if this X is smooth, uniformly smooth, with smoothness like that, Q stands here, then we guarantee that the entropy numbers in this one, and this again, it is a weaker norm. It's a norm, like I can say that the dual to this will be sort of L infinity, because see, this is sort of L1, and that is sort of L infinity. But it's kind of just waving my hands, but just to give you some intuition. But rigorously, this is that, and we have this this inequality, this bound for the entropy numbers. And again, k to the exponent. It turns out that this is the dual. So when we apply this, we use x as a dual, and then we would get 1/q here. But again, a small remark here, that it turns out that this log n here can be replaced by log n divided by k. And if you do that, then you cannot improve that, because it's not just an example of unit balls in Rn. You will have that it cannot be improved because those results are known, and this is the n. Okay, let's keep going. Now, as I promised, if I have, and I do have like 15 minutes, I will explain some relation between this numerical integration, but mostly for classes, and numerical integration and discretization. So this is just a notational thing. Everybody understands that numerical integration is something which allows us to replace integral by the Kubacha formula. Again, this is just a terminological thing. In RG, d greater than or equal than 2, it is a cubature formula. In R1, this is quadrature formula. And basically, this is just a notation. So the cubature formula are designed with points and with weights. So here we assume. So now it's interesting that some property which people did not really pay attention to, of function classes, are important in this discretization. What is that property? We call this quasi-algebra property, and it's not in the literature. In the literature, it is called, and let me give this point here. So this kind of property is called multiplication algebra. This is what Hans Triebel used. But what is the property? The property is that this W class, we say that W class has this quasi-algebra property if for A and for two F and G elements from the class, their product is basically also in that class, but maybe rescaled a little bit, divided by this A. And I prefer to use this quasi-algebra property because Hans Triebel writes also that it is algebra, and this, but it's not really algebra because for algebra A should be 1. But this is why I think it's better to call this quasi-algebra. But anyway, for our purposes, when we try to solve these problems in the sense of order, it clearly doesn't matter. Even if this holds with A equals 1, we will not, it will not help us much. So just constants will be better, but we don't care about those constants now. So, but anyway, this is the property. Now, the proposition. It's a very simple proposition, straightforward. Everybody can see it, and in 5 or 10 minutes, we'll prove that proposition. So if this W has a quasi-algebra property, and in addition, we have this property is just for complex case. If you're talking about the real case, we don't need this property. Then we have this inequality. So that means exactly this is what we talked about. We integrate the square of the function and apply the cubature formula to the square of the function, and we guarantee the upper bound in terms of the worst case error of the cubature formula on the class W. So this is discretization error, and this is integration, numerical integration error. So now let me give some examples in order to be more specific. So this is general proposition, which is very straightforward, very simple. But what kind of classes we can consider? So let's consider periodic functions, and which are expressed in a certain way, but first some notation. So these are Fourier coefficients, and we consider the class of functions, which are represented in this form. So that means it is a convolution of functions. It is in L2, so functions which are in L2 bounded, and it's not a class yet, it's space, but anyway. So many of the classes which we discuss and which we study in approximation theory, when it comes to periodic functions, they have representation like that. But here, F is kind of general function, general kernel. And we define, under this assumption, we define the norm in this space like this. Again, it's standard. Usually the class is the mapping by this operator of the unit L2 ball. So this is kind of natural thing, and this is what we will do. We will define, again, use the same notation for the unit ball in this space. So, and this will be our class. This will be our class. So in that case, if we do that, then basically the question about this quasi-algebra will be this one. So we take two functions in this class, and now we take a product, and we evaluate this norm, and we want to have this. So clearly, this can be expressed or can be proved under some conditions on the Fourier coefficients of this kernel F. And this proposition is, again, very straightforward. So if this condition is satisfied, then we have a quasi-algebra property. So what specific classes do satisfy this assumption? It turns out that the function classes with bounded mixed derivative, and we are talking about L2 only, so these classes, they do satisfy this quasi-algebra property. And what are these classes? We define the Bernoulli kernels. So these are FRX as follows. This is just a notational thing in order to avoid division by 0. And these are the Fourier coefficients. And as you can see here, that basically the product of absolute value of kj's. So they are decaying, like the level curves for these will be hyperbolas. And this is what is related to hyperbolic cross approximation and other stuff. So these are function classes with bounded mixed derivative. And it turns out that indeed these classes satisfy that condition 7. See, with restriction r greater than 1/2. But for these classes, this restriction is very natural because this is a necessary condition for embedding of these classes into L infinity. So in that case, only we can evaluate the functions at each point. So we have this property, and it turns out that, let me give one more example. So now we have this class for all dimension D. But let's now switch to dimension D equals 2 in order to get some result, some very specific result. And the result will be the use of numerical integration with respect to the Fibonacci Kubacher formula. So this will be Fibonacci Kubacher formula. So this is only for D equals 2. And we define the Kubacher formula with respect to the Fibonacci numbers or Fibonacci points like this. So this means that this is the fractional part of this number, So it turns out that it's known, very well known, that Fibonacci Kubacher formulas are really good for numerical integration of functions with bounded mixed derivative. And it turns out, and this is known. So see, I write this. So this is the error of these Kubacher formulas on the function class, but our function class will be this, with bounded mixed derivative in L2. And this is known. This is known. It is a non-trivial result, but this is known. So, and this is the order. So that means this is upper and lower bound with two constants. So this sign. So the order is like this. So that means if you apply that and apply that proposition which I wrote about this quasi-algebra, so if you combine these two things, the quasi-algebra property and the bound for the Fibonacci Kubacher formulas, then we get from there immediately this bound. And it is a non-trivial bound because, as I said, this Fibonacci Kubacher formulas, that upper bound is a non-trivial one. So anyway, so we have this. So how about the lower bounds? So is this the best, or, and there's one question, is this the best? And another question, how to extend these results for D greater than 2. It turns out that we can do something, maybe not that accurate like that one, but still we can get something. It turns out that the following result holds. And now let's look at this more closely. So first of all, in this theorem, there is no restriction on D. So D could be any. D could be any. And then we get the order of this quantity. And this is the right order. So let's see what is that. But the difference between this theorem and the previous one is that here there was no this O. That means this is the one which corresponds to discretization, sampling discretization with equal weights 1/n. But this O here means that we allow weights and we optimize over points and over weights. So that means this quantity is always less or equal than the similar one without O. So I mean the lower bound for this certainly gives the lower bound for this quantity without O. So now if you look at this one and see D, substitute D equals 2, then you'll have 1/2 here, and this, oops, and this is exactly what we had as an upper bound here. So that means this discretization, and we can even say more, that discretization for L2 norm of functions from this class using the Fibonacci point sets is optimal in the sense of order, because the order for this class is this. But also we can complement these lower bounds by upper bounds. But again, going from g equals 2 to g arbitrary, we pay this price. So instead of nothing here, that means equal weights 1 over m, we need to allow the weights in that Kubacher formula. But anyway, the sampling discretization for this class is of this order. So now we know that. So, and basically the final thing, how we prove these lower bounds. Again, these lower bounds turned out to be related to numerical integration lower bounds. But we need some property. Again, this is very simple property. Now it's written in sort of general terms. So we define two functions and we assume that the class has this property. That this function, if f belongs to the class, then this function belongs to the class, and the same here. But this is a remark that if W is a convex set which contains function 1, which is always the case in all the applications which we consider like specific function classes. So that means this property A is automatically satisfied. So now notational thing, and then I will formulate this here. This is the best error of Kubacher formulas. And as you can see here, we optimize over points and over weights. So this is the minimal error for numerical integration of functions from the class W using m points and clearly m weights. So, and this I knew just to explain that this is integration and this is the Kubacher formula. Then it turns out that using it's again not, here is some observations needed, but anyway, it's comparatively simple observation. I mean, this theorem, that if the class W has property A, then we have this lower bound. And this lower bound is stronger than if we do not have O here. So that for any is lambdas, for these weights, for any discretization like that, we have this lower bound. And again, these ones, again, it's non-trivial result. For classes W R2, these things are known. So this is how we got those results in there. And I think that's it. Thank you very much.
Thank you, Volodya. Thank you. You finished 2 minutes earlier, but it's very good. Thank you. But any questions or comments, please? If nobody is ready, I have one question. Maybe it's more close to Yegor, but with Safriri, we consider the norm which is weaker than what you use. I mean, it's integral uniform norm. We take uniformly distributed n points and then take maximum of the function on this set and then integrate over all system of points. So is it possible that such kind of norm could be used, you can use in this area?
But I don't know, because as to this one, as I already pointed this out, that means with this comment, that basically in that, so there are different proofs. So for instance, this result with this improvement, I use a different way to prove, not the way which Talleyrand used. But anyway, this is important, and in his proof, it is important too, that basically this function evaluations are in a certain sense dual to that L1 norm. So that is kind of, because the whole theorem, this theorem is about duality. So
Okay.
But
Maybe we shall discuss it.
maybe
but
your
when you do something more complicated, like you said, I don't know what will be the dual norm to that, and I don't know if you could do something, because the basic and the very important thing here, like in this setting, again, it's hidden in the proof what I used here. We use some comparatively deep results from greedy approximation. That if you have the unit ball like this, then we can approximate it well in the sense of M-term approximation.
Yeah.
And then one more result about entropy numbers. So basically, on several steps, we do need this specific property that is A1 here and L infinity dual to this, like L infinity function evaluations. So I don't know.
Okay, we shall discuss it later, because
Yeah.
but Sergey,
Maybe it is possible, but even if it is possible, it will be non-trivial.
Yegor would like to say something.
I think that the answer to your question will be in my talk.
Ah, okay, because okay, because you see, we got the low estimate for random processes with this norm, and people from school of probabilistic, they couldn't do such a low estimate because it's a weaker norm. So for me, it was maybe it's useful for something else, but I don't know. Okay, thank you. Any more question? If not, thank you.
Да, запись выключай. Значит, Владимир, please stay here, как говорится.